seconds. Right. I think we've got a couple more people still filing in, but can get started. So yeah, welcome everyone to the 36th ECS and Cloud Feedback Virtual Symposium. And today we've got a slightly shorter session. We've just got two speakers. So that means we either have more space for discussion or people can get to lunch slash dinner slash late breakfast a little bit earlier. So to remind people of the format. So, oh, I forgot to change this. So we're going to have two HU style talks, 12 minutes long. So I'll just unmute myself and say 2 minutes when you have 2 minutes left. We'll have some short time for questions, and then we have after each talk, and then we have a general Q&A at the end for further questions. You can put questions in the chat at any time, and then you can raise your hand and we'll unmute you if you'd like. And this is a shout out to the rest of our executive committee. And we also have, if you're not aware, we've been doing these talks, for 3 years now, and so over 3 years, and so there's a backlog of really exciting material if people want to go back and listen to some other sessions. So with that, I'm going to pass it off to Ben Mackay, who is a PhD student at the Scripps Institute of Oceanography. And he's going to be talking about how sea ice warms the Arctic. So yeah, take it away, Ben.
Great. Thank you, Andrew, for inviting me, and thank you to the rest of the organizers for putting on this symposium. Yeah, today I'm going to be talking about how sea ice warms the Arctic climate. And I'd also like to thank my collaborators, Lily, Ian, and Changping here at Scripps. And let's click through. Okay, great. So why do we care about sea ice? Sea ice is a kind of striking feature of the Arctic climate, and it's rapidly changing. And we've been able to observe these changes since the onset of the satellite era. So on the right-hand side, you'll see a figure of the sea ice extent in September, which is typically the annual minimum in sea ice extent, and that's been steadily decreasing since the beginning of the satellite era. And the fact that sea ice is changing quickly kind of poses two related questions. The first is, how does sea ice affect the mean climate state in just in an equilibrium climate under normal circumstances? And when the climate is changing, what role does this observed sea ice loss play in that climate change? And I'll start by focusing on this first question of how sea ice affects the mean climate. That's the bulk of this talk today. And if you were at AOFD this spring, a lot of this will be familiar to you. And to be answering these questions, I'm going to be using a CSM1 slab ocean model. So this is a full atmospheric model coupled to a simple motionless slab ocean, which is just a thermodynamic mixed layer with prescribed ocean heat flux convergence. And on top of this motionless ocean is a kind of full thermodynamic sea ice model. And importantly, this ice, even though the ocean is motionless, this ice can move around on top of this slab. Ian likes to call it a slippery slab. So this ice is drifting around because it feels wind stresses from the atmosphere and also prescribed ocean currents. So how can we use this model to isolate the role of sea ice? Well, the first thing that a lot of people would think of is to simply disable sea ice formation and compare an icy world to an ice-free world. And you can do this several different ways, but what we do is we just crank the freezing point of water down enough that ice no longer forms. And so then we have on the left an icy climate, and we compare that to an ice-free climate on the right. And as you might expect, contrary to the title of my talk, sea ice does indeed cool the Arctic. On the left-hand side, you'll see the difference in surface air temperature between the icy and ice-free world. And the icy world is much colder than the ice-free world. And this is because the sea ice albedo changes dominate the response to sea ice loss. So that albedo effect of ice really does cool the Arctic climate, as we all are used to thinking. But what if we want to look past albedo to some of the other effects of sea ice and understand some of the other physical processes that ice influences? We can, instead of simply disabling sea ice formation, we can go a step further and prescribe the albedo from our icy world on the left to our ice-free world on the right. So in our case, we take the monthly mean albedo from our icy control climate and prescribe it to our ice-free world. So this is a temporally and spatially varying albedo. And essentially, you're painting your ocean surface white, so there's no ice there, but it still has the same kind of shortwave radiative effects, reflectivity. So now what happens if we take the difference between our icy world and our ice-free world with the same albedo? What we found was a little surprising was that the sea ice, the world with sea ice, our control climate, was warmer than our ice-free climate with albedo prescribed. So you see that in this figure here, where there's some fairly strong warming over the Arctic basin and a little bit of cooling in East Greenland, which is a key feature that we'll talk about. But this took us a little bit by surprise, and we were scratching our heads for a bit trying to understand why this might be. And the first mechanism that we really got our hands around was sea ice export might be playing a role in this. And the big idea being that sea ice export, ice moving out of the Arctic Ocean throughout the year, effectively transports heat poleward. And this is because you can think about this in a few ways, but I like to think about this as ice forms at high latitudes and latent heat is released during this formation. It's then pushed equatorward by your ocean currents and winds, and then it melts in those warmer lower latitudes and takes up latent heat. And so because your ice melts and your ice freezes and your ice melt at different places, that latent heat is not taken back up in the Arctic. So you have this heating due to ice motion. And a clue that this was indeed happening came from the model. So on the left-hand side, you see again this same difference in surface air temperature between the control climate and the ice-free climate. And on the right-hand side, you see this is just the control climate, the sea ice and growth, the sea ice growth and melt tendency. So the red area is where more sea ice grows than melts throughout the year. And that's where you would expect this latent heat release. And the blue area is where ice has been pushed out of the Arctic. This is the ice export pathway, kind of along this east coast of Greenland. And that's where your sea ice is predominantly melting rather than forming throughout the year. So that's where your latent heat is being taken up. And this matches really well with the pattern of warming and cooling that we were observing. So we wanted to then, we're thinking now about ice motion. How can we really put a finer point on this? Well, we actually decided to disable ice motion in our model. And I'll step you through the set of simulations that we used to isolate the effect of ice motion. The first two simulations are the ones we've been looking at so far. A control climate with all these simulations have pre-industrial levels of CO2. A control climate has an active sea ice model. The ice is allowed to move around. Albedo comes from that sea ice. And then we have this no ice albedo from control model, which is the prescribed albedo case where it's ice-free, but albedo is coming from the control model. And so if we take the difference of those two, we get kind of a total ice effect, not including the effect of albedo, since that's the same between the two. And then we disable ice motion, and there's a handy little toggle in CSM that allows you to do this, but it essentially the ice doesn't feel any momentum fluxes anymore. Those ice motion tendencies are never updated. So the ice velocities are always zero. So you just have ice growing and melting in place. So the no motion case, you have this actively growing ice model that doesn't have any motion. And then again, we have an ice-free model with albedo prescribed from the no motion case. And so the difference between these two then gives a total effect of motionless sea ice. And then hopefully you all see where this is going. If we take the difference between our two differences, we have a total ice effect from our first two cases, a motionless ice effect from our second two cases. And the difference should give us a handle on the role of ice motion. So if we do this, we indeed find that ice export is warming the Arctic. The role of ice motion is to warm the Arctic basin. And so we see a few degrees of warming over the Arctic Ocean. And we again see this expected cooling in the ice melt corridor by Svalbard and East Greenland. And we wanted to just kind of roughly quantify the magnitude of this export. And we did this by simply find the ice heat transport through the 70 north latitude circle. And we did that by finding the ice volume transport through that circle and converting that volume of ice to a heat by multiplying by the latent heat of fusion and the density of ice. And then you distribute that over the area of the Arctic. And in our model, the slab ocean model, we found that it was around 2.5 watts per meter squared over the Arctic of heating. And we wanted to compare this to a fully coupled model with an active ocean. So we've looked at the CSM1 large ensemble, and it had a pretty similar magnitude. So enabling ocean dynamics didn't play too much of a role in modifying that value. So yeah, this we understand pretty well at this point. We feel that this ice export mechanism kind of behaves as we would expect it to. But it's not the only effect going on here. And so you remember earlier that we had a motionless ice case. And so we found that there was still warming in the Arctic, even when ice is not allowed to move around. So on the left-hand side, we again see this surface temperature map of the motionless ice case versus the prescribed albedo case. And there's warming pretty uniformly across the Arctic. On the right-hand side, we compare that to, we just took a zonal mean. The red line is this motionless case. The blue line is the effect of ice export that we were just looking at. And so indeed, even without ice motion, there's an even greater warming effect than simply the export mechanism we were looking at. So we've been using the radio feedback framework to investigate this. I'll really quickly step through this. We have a radio forcing perturbation that we apply to our climate system. There are then feedback parameters that might amplify or damp warming that comes from a forcing. We have a surface temperature change and changes in ocean heat uptake and heat transport. In our case, rather than applying a radiative perturbation, we are perturbing the sea ice cover. So we're looking at the changes from an ice-free climate to an icy climate. And we've been finding that what we believe is causing this warming from motionless sea ice is that there's seasonality to these feedbacks, such as the lapse rate feedback or cloud or albedo effects or water vapor, but particularly seasonality in the lapse rate feedback is amplifying summertime warming. So on the left-hand side, we just have the seasonal cycle of temperature. In the red is the icy world. There's a much more dramatic seasonal cycle. Blue is the ice-free world with prescribed albedo. And we believe that, seasonality in our lapse rate feedback, particularly during the summertime, amplifies warming when we add ice to our model, leading to a shift in the annual mean temperature. So the red world has an higher annual mean temperature than the ice-free blue world. And our feedback analysis is indicating that this is predominantly coming from the lapse rate feedback. And we still need to put a finer point on this. This is pretty preliminary work. And I will wrap it up there. I have more slides on CIS loss in the future and the roles of export in the future, but this is kind of up to date as far as how CIS affects the mean climate. And it does this via the CIS export mechanism, transporting heat into the Arctic, and then these seasonally varying feedbacks amplify the seasonal cycle and temperature to lead to annual mean warming as well. So thank you for having me. Happy to take any questions.
Thanks, Ben, for the very nice talk. Any questions? People can unmute yourself and speak up directly or put it in the chat. Delso? I might have mispronounced your name, but please go ahead.
Nice talk, Ben. In regards to this point about the annual cycle, if it's just a pure sine wave, that would not change the mean. So I think you have to have an argument that says that somehow the asymmetry in the annual cycle is changed. Have you thought about what that, and maybe you said it and I missed it, but did you have an idea of what the asymmetry is that causes that?
Here, let me try to get back a slide. Okay, let's get here. Okay, you can still see the slides? Okay.
Yep.
Yeah, so you can see that there's, so if we're starting from the ice-free world and we're then adding ice, we're starting from this blue sinusoid, as you say. What maybe we need to show here is that, and what we indeed see, but I don't have a plot of here, is that there's a seasonal cycle of these feedbacks and the strength of these feedbacks. And so the lapse rate effect is much stronger in the summertime, in this case, than the wintertime. And that's going to amplify your summertime warming compared to the wintertime cooling, leading to an asymmetry because your strength of the feedback is not constant throughout the year.
And why is the lapse rate feedback stronger in the summer than winter?
Yeah, it's because in summertime in the ice-free world, you have a pretty strong inversion, and in the icy world, there's a weaker inversion. And so there's a bigger difference between, I think there's a bigger difference between those two, the temperature structure in the lower atmosphere in the summertime than the wintertime, when in both cases you have a fairly strong inversion. So there's a bigger difference in that temperature structure in the summer, which I think is amplifying warming. But again, we need to put a finer point on that.
Okay, great, thanks.
Thanks. I do miss your question from the chat, which is interesting, I think. So they ask you, when you prescribe your sea ice in your model, how do you prescribe the ice thickness?
Yeah, so in the icy worlds, ice is fully active. So the ice thickness and ice is not prescribed. But in the ice-free worlds, we're just prescribing albedo. So it's either fully active ice model or it's just prescribed albedo in an ice-free world. Hopefully that helps.
Maurice, I see the hands raised.
Yeah, hi, thanks for the talk. My question is, you said that when you make the CS disappear, you just lower the cooling point, the freezing point, so low that ice doesn't form, right? But in reality, one of the effects of the ice is that it allows air temperatures to drop below freezing point, right? And I think in your setup, that wouldn't make a difference then anymore. So in reality, I would expect the sea ice actually to allow the surface temperature to drop much lower than if there would be no sea ice. So I wonder if you could comment on that maybe?
Yeah, we certainly see that. You can see that on the right-hand side, and where in the wintertime, your icy world does allow you to get a much colder wintertime temperature than the ice-free world. Because again, yeah, as you say, it's shutting off the connection between the ocean as a heat reservoir and the atmosphere.
would your effect disappear if you didn't allow the temperature
you-
to drop below freezing?
So in that case, you're like, you just are shutting off the connection, or
Yeah, I don't know how that would work.
yeah, I'm not exactly
I
sure
haven't
how
thought
you
it through in
frame that,
detail.
but yeah,
Yeah.
that's definitely like, I think like the effect of ice to tie temperatures to that freezing point really does play a role. Yeah.
I think the reason I'm asking is because I was like double confused when you said that ice warms the Arctic, because I expect ice to, because my expectation was ice to cool the Arctic also in regards that it allows surface air temperatures to drop well below zero. Well, if you don't have ice, you can't really have that. So
Yeah.
but I have to think about it more. Yeah.
Right. So that's definitely happening in the winter, but what we're finding is that the amplification of temperatures in the summer is greater than the cooling of temperatures in the winter, which leads to, in the annual mean perspective, a warming. So maybe a warming in the annual mean sense, but seasonally, it definitely leads to cooling too.
Yeah, thanks.
All right, there are more follow-up questions about ice thickness in the chat. But for the interest of time, we can move on to Anna.
Yeah, and are you able to share your screen now? Yeah, great.
Yeah, is it up
Cool.
now?
Yep.
Yeah, perfect. And
Cool.
hopefully full screen in a minute. Now?
Yeah, and yeah, I'll introduce you as well. But and we've got Anna Mackie now, who's going to talk about circulation and cloud responses to pattern warming. And Anna is a postdoc at the University of St Andrews in the UK.
Great. Thanks very much. Yes, so I'm Anna. I'm from the University of St Andrews, and I'm going to talk about some work that me and my co-authors have been doing about circulation and cloud responses to pattern warming. And as you might have guessed from the title, this is to do with the pattern effect, which I'm sure many of you are very familiar with. But I just wanted to run through the kind of the main mechanism to make sure we're all on the same page. Essentially, we're comparing cloud feedbacks in response to two different patterns of warming, and I think it's really nicely illustrated by this schematic from this Rubinstein paper from last year. So we take sort of the first scenario where we have sea surface temperature warming in convectively coupled regions, such as the West Pacific. The warming here is able to raise the free tropospheric moist static energy, allowing it to have remote effects. For example, in climatologically subsiding regions, such as the East Pacific, where we would get an increase in low cloud cover, and this would lead to a negative low cloud feedback. And we can contrast this to the sort of the opposite, where we're warming in these climatologically subsiding regions, such as the East Pacific, which might have a temperature inversion, which would lead to this sort of warming becoming trapped. So we're not raising the free tropospheric moist static energy. We can't have these remote effects. And locally, we might find there's reduced stability, a loss of low cloud, and a positive low cloud feedback. So these contrasting cloud feedbacks are associated with different patterns, and as we all know, there are impacts for estimates of climate sensitivity. But what I want to address today was the previous schematic showed cloud responses from climatologically subsiding regions, but what about cloud responses from other circulation regimes? And how might these circulation regimes change with pattern warming? And to do this, we use a set of AOGCM simulations from ICON and with idealized patch warming. So these were published last year in this Willens et al. Paper, the Circus paper. And we're using a subset of these simulations. So control simulation with AMIP SSTs. There's 4 different patches perturbed, each between -4 and +4K in steps of 1K. We've got 10 years of data and we're using climatological monthly means. The domain I'm looking at is 20 south to 20 north, and I'm only looking at ocean points. So this figure from the Williams et al. Paper shows the location of the patches, and kind of the key takeaway was that you get these differing top of atmosphere responses depending on where you warm, and that this response was non-linear. So I'm just going to talk about two patches today, 180 East, which is broadly speaking a region of convection, and 220 East, which is broadly speaking a region of subsidence. I just wanted to start off by showing the a sort of a bulk circulation metric, ascent fraction. So ascent fraction is very simply the proportion of the domain which is ascending at 500 hectopascals. And we can see that using this very simple definition that we have very different responses between the two patches. So in the 180s case, we get this contraction of the ascent region with warming. And in the 220s case, we don't see very much happening across the temperatures. And we want to dig into this a little bit more. And to do this, we use a moist static energy framework. So this is a very straightforward idea. Essentially, on a grid point by grid point basis, we ask the question if the surface moist static energy is higher than that at 500 hectopascals. And if it is, we assume it's ascending. And if it's not, we assume it's descending. So we can very simply model ascent fraction as the proportion of grid boxes which have a sufficiently high surface MSE to overcome this energy barrier. So how does this index work? Does it work? This is the control simulation where the color scale is this instability index. So the blues are estimated to be ascending, and the dashed line is the 0 line. So it sort of shows the ascent region. The solid line is ascent fraction as determined by vertical velocity at 500 hectopascals. So if our index were perfect, the dashed line would sit on top of the solid line. So you can see it's not doing a bad job. It's generally finding the right region, but it has a tendency to overestimate, especially in regions like this. So we did a bit of digging at sort of what characteristics the kind of incorrectly identified as ascending points were, and we found that they were generally dry air. And this suggests a role for the entrainment of dry air. So we go back to my little doodle. I was essentially assuming that the moist static energy doesn't change as we go up through the troposphere, but of course you might be entraining dry air, which would have the effect of reducing moist static energy potentially below the 500 hectopascal saturation level. So to include this into the instability index, we use the zero buoyancy plume model of Singh and O'Gorman from 2013. And this relates the rate of change of moist static energy with altitude to the saturation deficit. And so very simply, we integrate this equation from 500 hectopascals down to the LCL to estimate how much MSE is lost through this entrainment process. We also had to estimate this entrainment parameter E hat, and I'm happy to talk about that if anybody's interested. And we find that this really improves things. So this is the same month of the control simulation, and we can see that the shape is much better captured by this instability index. So there's still some bits which are misidentified, but on the whole, it's doing a pretty good job. So this is just the control simulation. The real question is, can we recreate those changes in ascent fraction that I showed earlier? So that's what this is showing. These red curves are the same curves that I showed a few slides ago. It's ascent fraction as determined by vertical velocity of 500 hectopascals. This purple line is the ascent fraction as estimated by our instability index. And we can see that it's doing a pretty good job. We're able to capture this contraction of ascent for the warming perturbations in the 180 East case, and there's kind of not very much happening in the 220 East case. So now we have this instability index, which we think does an okay job. But how can we use it to look at cloud response? And I think it's helpful to just start with a PDF of the instability index of just the tropics-wide domain. So this is blue line. We can see that it's peaked in the positive, so that's the ascending region here. We're then going to apply some patch warming. I'm going to look at the plus 2K simulation, and that's going to be in two different patches. And I think it's helpful to think about these patches in this instability space as well. So in 180th case, that's this red line here. We can see it's peaked very strongly in the ascending region. While in the 220th case, we have a much broader peak with many more points in the negative, so the subsiding region here. We're then going to take this blue line and for each discretized grid box on the x-axis, we're going to further discretize according to the instability index after the perturbation has been applied. And that looks like this. So there's quite a lot going on here, and I'm going to talk you through the main features. So the first thing to point out is this x-axis is exactly the same as I had in the previous slide. It's the control instability index. And the y-axis is this perturbation instability index. So the point lies on this dashed 1, 1 line. That means its instability index hasn't changed as a result of the patch warming. If it's above the 1, 1 line, that means the stability has decreased. And if it's below the 1, 1 line, that means the stability has increased. And immediately we can see these remote effects. So by remote, I mean it's not lining up with the patch PDF, this red line. We can see all this spread around the 1, 1 line in the 180 use case, which we don't see in the 220 use case. I think it's helpful to think about this in terms of quadrants. So I'm going to refer to this quadrant up here as up, up, because it's ascending in both the control and the perturbation. So it's positive in both axes, and it's accounting for 33% of the domain. Likewise, this is down, down. And if we are interested in what's causing the ascent fraction to change, then these are the boxes that matter. So this is up, down. They're points that were ascending and are now descending. And this is the opposite. Were descending, now ascending. And it's the difference between these that changes our ascent fraction. And again, we can see a big contrast between the two patches here. So this has 15% and this is only 4%. And what we can do is we can take these points that fall into this quadrant and we can look at them more closely. And we essentially find that the changes in moist static energy at 500 hectopascal outpace those at the surface. So we sort of attribute this ascent fraction change to an opt-anti mechanism. This is just for one temperature perturbation. And what we can do is we can see how the proportion in each of these quadrants changes with temperature change. So that's these plots here at the bottom. So the dashed line here is the +2K simulation that I'm showing. And if we look at the up-down quadrant, so these like convective margins, we can see that as we warm, that this proportion increases, and this is accounting for the ascent fraction change. So this is circulation change, but what about the cloud responses? This is the same plot, but now instead of having a PDF as the color scale on the top here, I've got delta net CRE. And I think there's a few things that really pop out of these plots, E and F, and I'm just going to talk about them. So the first one is this region here, which are essentially the pattern effect points. These are points which are subsiding in the control simulation, so they were stable to begin with, and they've become more stable as a result of the warming. They're below the 1, 1 line. They've also got a negative net CRE. They've got the brown color. And if you're interested in the location, I've just plotted the location as the hatching here for January. And if we take this whole quadrant and integrate for this temperature to see how it's contributing to the tropical mean, that's this black line at the bottom here, we can see that this quadrant, this brown contribution, is making really quite substantial contribution to the tropical mean trend. But we do have contributions from other cloud regimes. So we also see a contribution here from this up region. Again, the location's up here. And we take this as being as an intensification of convection. And this is, again, another substantial contribution. And then finally, we have this small orange wedge here, which are these convective margins that I discussed earlier. And again, here we can see in the plot that they are indeed at the margins of the convection. And they're making a smaller, but still there contribution in this 180 east case. Yeah, so if the sort of the key takeaway, I think this instability space is very useful for looking at this patterned warming, and it reveals the contribution of different circulation regimes in response to patterned SST warming. Sort of to summarize, we developed a simple framework for estimating ascent fraction using moist static energy, and we use this to examine circulation and cloud responses in instability space. We find contrasting circulation responses depending on the location of the SST warming. So if you have warming in ascent regions, this leads to a contraction of that descent region, which we attribute to an opt-anti effect. And we find there are contributions of different regimes to the tropical mean delta CRE trend. So most substantially from the pattern effect and deep convective regions, but also a small contribution from the convective margin. So that's me, and yeah, thank you very much.
Thanks, Anna. Very good framework, very nice talk. I do see one question from the chat from Carson. He says, I'd love to hear how you estimate the entrainment coefficient. Which metrics are you considering? I suppose it's not too dissimilar to the concept of ECAPE.
So I'll just go back to the slide with the equation. Sorry, the sun has come out in Scotland and I can't see anything now. This doesn't happen very often. So essentially what we did is was I calculated this this H star entrainment from this equation here. And then I found the value of epsilon hat, which minimized the difference across the 12 months in the control simulation with the actual ascent fraction, if that makes sense. So I had the ascent fraction as calculated across the 12 months, and I had the rest of this equation, and I just found the E hat, which matched those as closely as possible. And if you're interested, that's about 0.18.
Great. We have another question coming in the chat from Tim. What happens in terms of the ascent fraction and instability index for a uniform SST warming, not patch?
That's a very good question and one which I would like to answer, but I don't have any simulations for that at the moment, but definitely something I'd be interested in looking at in the future.
Cool. Any other questions? Either for Anna or Ben. Let's see. Maybe I can start with mine. I do have a question back to Ben. Yeah, about your experiments. So when you talk about non-ice albedo effect, the first thing that jumped to my mind is maybe CIC insulating effect. How do you think this ice insulating effect would play a role in your results?
Yeah, we've definitely seen that ice insulation does change. Certainly when you remove that insulating layer, you do allow for greater sensible heat connection between the ocean and atmosphere. So there are changes within that ocean heat uptake term. Yeah, so you get more heat release in the winter from the ocean than you otherwise would, right?
Yeah, because if you remove the sea ice, but still considering the ice albedo effect, that means in the colder months, essentially you switch it to a different regime, right? Where you have the direct open ocean that will allow direct air-sea interaction or coupling or heat transfer, etc. I don't know. I was just wondering.
Yeah, absolutely. I mean, I
It
think
shifted
that's
to a different regime.
You definitely do. I mean, and we see that in the seasonal cycle as well. Like it's the amplitude is much more damped because you have that constant connection with that large, yes, kind of sluggish ocean reservoir of heat. Yeah.
Thanks. Well, any other final comments, questions for Anna, Ben?
Can I ask I guess I have one simple question for Ben. So like when you think about like, ocean heat transport and atmospheric heat transport, so when we do that traditional decomposition in the model or something, is this ice movement, is that aliased into is that part of the ocean heat transport?
Yeah, so
and I just never realized it, or
yes, so that's true. I'm gonna pop up my last slide one more time. Okay, So you can see the ocean heat uptake term here in our little feedback plot. And so you can see that when you take the difference between your ice-free and icy worlds, that ocean heat in a slab model, this ocean heat uptake should be prescribed and should be the same in all the cases, and it shouldn't be changing. So it should sit right here at 0, but you see that does change when you have ice motion. When you go from the ice-free to icy case, there's a shift in that ocean heat uptake. And this gap here is your ice heat transport. So if you separate that out as a different term, this will collapse to 0. Yeah. So that's, yeah, spot on.
That's cool. Yeah, and then we have a comment from Hung about the ascent fraction response to uniform warming, which is talking about it. So I think the idea is that you have a uniform SST change, that's a nonlinear MSE change. So MSE gradients will steepen under uniform warming. If you look at if you just look at the AMIP and AMIP plus 4K simulations, and you define ascent fraction based off of like the fraction of points which have monthly mean omega 500 going up, it's kind of like Gaussian around 0. The change in that is like Gaussian around 0. So I don't fully understand how to reconcile, like the MSE gradient picture, I think makes sense, that is intuitive and makes sense, but it doesn't seem to play out, at least in terms of this method, in this particular metric of ascent fraction. So I don't know, maybe using the entrainment adjusted one is better, or reconciles that somehow. I don't know.
All right. If no further questions or comments, I think we can wrap up earlier today. Give people back 15 minutes. Yeah. One more thing is we do have our speakers lined up for the next event, September, and we'll have Kate Marvel. I think it's Ariana and Nathaniel, right? Yeah. We will send out the email soon, and stay tuned. Other than that, thanks our speakers most again. I guess we'll see you next month.
Thanks, everyone.
Thanks.
Yeah. Thanks, Anna. Thanks, Ben. Those are great talks. Oh, Ben's left.